All right. A minute ago. Let me explain what a normal is. All right. What the normal to a surface is. Here's my calculator. Okay. I gotta remember that I just gotta hold this way and look at the green light so that I don't get all. Here's the flat surface of the calculator. Okay. Here's the flat surface of the calculator. Now, here's the normal to it. The normal is like this. So when this thing rotates, notice how the normal is rotating. Okay. Or if it's flipping towards you. That's what we the orthogonal plane. All right, it's 90 degrees to the plane of the surface. Represent the outside of my represented a coil of wire. This would be the normal to it, by the way. All right, good. So that's what they're talking about with the normal. When the normal is perpendicular, and we're looking at the top view of this thing. So when the normal is perpendicular to a magnetic field like this, it'll spin. Okay? And as it spins through, but then look what happens when the normal is parallel. When the normal is parallel, you've got a torque force going this. And is this true? Well, yeah, I've got the current going in, got the magnetic field coming out. The torque on this wire at that point is shooting down this way. The torque on this wire is shooting up this way. What's the net force? 0. Is there any torque on the wire at this point? No. So it all depends, rotates, that its normal becomes aligned with the magnetic field. Then the forces go to 0. But it's got enough momentum to get through there. All right? In other words, the torque gets less, maximum torque, 0 torque. And it'll start to pick up again. Maximum torque, and it'll spin at a constant speed because of the conservation of momentum. All right, so now, here's what happens. So the net torque on this thing is ILB 1/2 W, which is times the sine of theta. What are we calling W? Gosh dang it, I hate it when I do this. Oh, the width. Width sine theta. LB. Notice L times the width. L times the width. L times the width becomes A. The area. Okay. All right. So L is the length of the wire. Spinning. Or is that omega? Oh, I hate to do that to you. Yeah, LW, L times the width. Yeah, okay. So I'm sorry about that. And it's not trying, and I'm not gonna be so condescending to you and say, well, when you try and make it simple, no, this stuff is just hard, and sometimes I have to go back and review and go, oh, yeah, that's right. All right, but actually, like I said, the mathematics of it is not that bad. So it says a coil of wire has an area of 2.0 times 10 to the -4 meters squared, consists of 100 loops, and so here's the magnetic moment. This is what determines the torque. Put a bunch of loops in there. This is the number of loops. This is the current. This is the area. So there's all kinds of ways you can increase the torque. You can increase the number of loops. That's normally how we do it. You can need more wire, okay? Increase I, increase A. So let's take a look at this guy. The only thing that's tricky about this, have we finished both pages of this? Can't believe it. We have. All right. Anyway, the first 2 pages. But anyway, when we look at this problem, the 6, 7 is supposed to just be 6. Okay. Now, they want the net torque when this angle is 35 degrees, which means they want the torque off the normal from here, which would be 55 degrees. So we know this. So here's what I want you to come armed with when we look at this. The magnetic moment and moment is something is an engineering term or a physics term that means spin that sucker. It's turning. What's the moment on it? Turn that lever arm or that seesaw. You got the magnetic. This is the magnetic moment, which is N, I, B. Here's N. Here's I. Here's B. Okay. Oh, NIA times B sine of phi. Okay. Where NIA is your magnetic moment. Okay, so now it's right at this 35-degree angle, but when we measure that with the normal, that's going to be 90 minus 35 is equal to 55 degrees. We'll use 55 degrees in this case. All right, and then that way we can find, we got N, we got I, we got A, we got B. And the hard part was finding that. This is our torque, and this is our magnetic moment. That was horrible, but that's okay. Now, here's the next thing we're going to look at. Here's the next thing we're going to look at. I was going to do it all with this. But again, the normal is coming at you out of the page here. So the normal on this thing is coming up. And then right here, the normal is parallel to the magnetic field. So the forces, the sum of the forces equals 0. Sum of the forces equals 0 here, but it does create a torque max. All right? That's what we're talking about earlier. Okay, so now, here's what we're going to talk about in the next video. In the last video, all right? In the last video, we're going to talk about that. Is this where we talk about how wires create their own? Yes. Magnetic field? Yes, we are. And this is where we get into the thumb rule. Okay? So we're going to stop here. And then we're going to talk about, well, let me show you real quick. Psych. Thought we were going to end, didn't you? Now look at this. Here's what happens. And this is part of Ampere's law. Okay? Ampere's law says this, that the parallel, if I've got a wire, I've got a current running, here's my current I, running through this wire, okay, that's embedded in this, you know, it's this funny looking thing like this, and then more of the wire comes out here. Okay? Well, that's going to create a magnetic field. That's going to create a magnetic field, all right, that's parallel to a magnetic field that's out there, okay? In other words, Maxwell's equations tells me that a current creates a magnetic field around it. That's what we're saying. And that magnetic field is equal to, so you get this parallel magnetic field to the surface that's going around it, okay? For any current geometry, it produces a magnetic field. Any current geometry. If I've got currents in a certain geometry, they're going to create a magnetic field parallel to dl is equal. It's actually an integral that we're doing here. Is equal to mu naught permeability of free space again times I. All right. Well, if I make this a circle, the sum, so I got the magnetic field, so I've got the sum, I'll just pull it out because it's constant, of dl. If I take all these little bitty dl's that are going around the circle, that becomes magnetic field is 2 pi r. And so I got mu naught I over 2 pi b. The b field is equal to mu naught I over 2 pi r. That's for a long straight wire. Okay? And it follows right-hand rule number 2. And we'll get into that on the next slide. On the next